All right, back to talk about theory of plate tectonics. The theory states that individual continents shift positions on Earth's surface. This is thanks to the lithosphere and the asthenosphere. The patterns between the continental shapes can be fit together. So very clearly, South America and Africa have very complementary shapes. All were at once a part of a single large landmass called Pangaea. So the original idea is that continents will drift, but we know that they're not just drifting aimlessly around the world. They are moving according to plate tectonics and seafloor spreading hypothesis. But what we think now, or what we suspect now, is that even Pangaea wasn't the first supercontinent, that the continents have produced more than one supercontinent throughout the lifetime of the Earth. So what evidence do we have to support this? Well, we have evidence through igneous rocks because they record the Earth's magnetic field strength and direction when they're formed. Basically, it locks in the alignment with Earth's crystal field upon crystallization, and as long as those igneous rocks exist, they're going to tell us information about a world we were never in. Earth's magnetic field varies in strength and direction over time. We know that because we can see that here in our rocks in layers. We've been able to record 22 reversals over the past 4.5 million years. So you can see here, this would be the oldest layer because at the bottom, the arrows are all pointing down. Then there's another lava flow, which is a reverse. And you can see that over time, the arrows are going to change direction, which gives us a little bit of information about the history of Earth, as well as the changes in our continental patterns, and a little bit more about seafloor spreading and our boundaries that we're going to talk about. So what about some evidence from the ocean? Well, one thing that we have that we can see now is called an oceanic ridge. We know that these coincide with submarine earthquakes, and there's rifting or separation along the crest. And there's a large amount of heat escaping from the crust, which the heat is probably coming from the mantle. Now, this is a really unique thing called the Mid-Atlantic Ridge. And the interesting thing about the Mid-Atlantic Ridge is that it is all underwater except for a very small portion of it, which is in Iceland. And it crosses the continent, and you can walk across the Mid-Atlantic Ridge in Iceland or walk through it. So what we know about the Mid-Atlantic Ridge is based on the fact that we have rocks that we're able to study the magnetic field to determine how old or young they are. So oceanic trenches are going to be long, narrow, and deep troughs with steep sides. They always run parallel to the continental edges, so you'll see them along the continents. Okay, and when we talk about ocean and things like that, we'll see oceanic trenches again. So what is this hypothesis that comes along with the Mid-Atlantic Ridge? The seafloor spreading hypothesis is the idea that hot molten rock moves up from Earth's interior, emerging along a rift, which just happens to be the Mid-Atlantic Ridge. Outflow in both directions creates new rocks. So the world is basically busting apart, and new hot magma comes up through here and forms new seafloor. We have drilling evidence to support this. We have thin sediment layers near the ridge, so right here, which becomes thicker the closer it gets to continents. There are older fossils out here near the continents, and then younger fossils down here near the rift, which suggests that things that died there more recently versus the ones that are near continents, which are much older. So we also have magnetic seafloor spreading evidence. Just like we use the layers of igneous rock to say oldest to youngest, we can do the same thing here. We can monitor oldest to youngest, and we can study the rocks in the exact same way. So this is called paleomagnetic studies, which show us that the magnetic strips in the ocean floor of basaltic rocks. The identical magnetic reversal patterns on both sides of the ridge, meaning if I took a rock here and a rock here, I'm going to see the same pattern. And it works all the way until the very center of the ridge. So these patterns that we see here match those found elsewhere that we know a lot more about based on current layers, provide age determination, which is important. And these are all estimations. No one really knows because no one was really there when it happened. That's why we call these things theories. So what this brings us to is plate tectonic theory. The basics of the plate tectonic theory is that the lithosphere, that rigid upper crust, is broken into fairly rigid plates. And these plates are going to float and move around on the asthenosphere, which is that semi-liquid upper part of the mantle. Earthquakes, volcanoes, and other rapid changes in Earth's crust will occur most often at the plate edges, but not always. Earthquakes and volcanoes can happen elsewhere for other reasons, but the majority of them occur along these black lines, black and white lines that we see here. Okay. 3 plate motions will commonly be seen here: divergent, convergent, and transform. So let's look at where some of these are. This is the North American plate up here in green. You have the East Coast, which is California, the Cascade Mountains, all of which are heavy volcano, either previously volcano, current volcano, or earthquake activity. You have the Andes Mountains, again, very similar. And then it goes along here in India, in the Ring of Fire as well, which is right there. Okay. So let's talk about the different types of boundaries. A divergent boundary is where things are moving apart. So this is our mid-Atlantic ridge. When plates are moving apart, it allows for magma from the asthenosphere to basically come up into the cooler area, and then it's going to solidify. And then as it moves apart, more magma is going to come up and create new crust. So because crust is being formed here, we're going to call it new crust zone. It's often accompanied by volcanic activity because volcanoes, again, are magma rising up from underneath. And the example we have is the Mid-Atlantic Ridge. Convergent boundaries are going to be when plates are coming together. And this is where old crust is destroyed in the process. So it's the opposite of divergent boundary. It's called, with the convergent boundary, there is what's called the subduction zone, which is where one crust is going to be pushed down under the other, and the material that's getting pushed down will partially melt and join back into the mantle. So hello, it's being recycled. There are 3 possibilities: converging continental and oceanic plates, so a continent and the ocean, 2 oceanic plates, or 2 continental plates. They're all going to produce different features that we'll talk about right now. So when we have an ocean-continent plate convergent, we're going to have a more dense oceanic plate coming together with a continental plate, which is less dense. The plate that's more dense is going to be pushed down underneath this continental plate, and the material that's going to be recycled is the basaltic material, and the granite is going to be preserved. Now, because that happens, it's going to feed the magma. We're going to see a lot of volcanic activity along these areas, and there's going to be a deep oceanic trench with deep-seated earthquakes next to these volcanic mountains. So the best example that I can think of is the convergence of the South American plate with the Nazca plate, which, if we go back and look, is right along here, and that is our Andes Mountains. When we have 2 ocean plates coming together, it's a little bit different because both plates are now made out of oceanic lithosphere, but one is still going to be pushed down underneath the other. But when this happens, we have a trench that's formed and an underwater ridge. The underwater ridge is going to be associated with deep-seated volcanoes and the formation of island arcs that form where the melted and subducted material rises up through the sea level of the overriding plate. So the plate that stays on top is going to then rise up and produce these island arcs. And the best examples I can think of are the Hawaiian Islands as well as the Aleutian Islands. The last one is 2 continental plates coming together. They're both made out of granite. They're both less dense, and so they're going to resist the subduction. There's not going to be any, one plate's not going to push down the other. So the colliding plates, instead of one being pulled down, they're actually going to pile up, which is going to produce a deformed and thicker crust of lighter materials. And these are going to produce really pretty mountains. The example that's here is the Tibetan Plateau and the Himalayan mountains. So if we go back to our globe, we can see them here. The Eurasian plate colliding with the Indian-Australian plate. Okay, so we have the building up. And so the question might be, well, if the plates are coming together, the mountains are continually getting taller and taller and taller, aren't they? But we've yet to address a particular issue with it, which is weathering and erosion, which is going to be the opposite process of this building up that we see with these plates converging. The last type of boundary is a transform boundary. It's going to occur when two plates are sliding past each other. Crust is neither created nor destroyed in this process, not officially. Things can be destroyed, but the crust isn't being produced or destroyed. Irregularities in the movement along the boundary will cause sudden jerks and produce earthquakes. So what happens is the two plates are smashed next to each other and they're pushing, and then eventually they're going to have enough pressure behind them that they're going to snap. And when they snap, that sudden jerk in the plates moving past each other produces an earthquake. The bigger the snap, the more pressure behind it, the bigger the earthquake. So the example of a transform boundary would be the San Andreas Fault along California. There's really neat images where you can see someone has built a fence over time, and the fence gets separated because the plates are moving past each other. It's not a very fast process, but it can be marked with time, which is a really interesting geologic feature to be able to see. Now this is going to end your chapter 15, so make sure you complete your notes and submit them when you are ready.